Welcome everyone again to another episode of the ideaXme show, that profiles the humans behind the really big ideas that are shaping our world, inspiring the future and future creators and thinkers and all those that like really great stories. I'm Ira Pastor, your life sciences ambassador for the journey today, though going to be wearing some additional hats. Call me your theoretical physics and cosmology ambassador today. Today we have a really exciting thought leader joining us who spends his time truly thinking about the big questions. Questions like, what is the origin of our universe? Questions like, what is behind this cosmological constant that Albert Einstein came up with regard to seeing this accelerated expansion in space? What determines the formation of galaxies, and a variety of other fascinating topics. We're honored to be joined by Dr. Vitaly Vanchurin, who is Associate Professor Theoretical Physics and Cosmology at Swenson College of Science and Engineering at the University of Minnesota. Dr. Vanchurin has both master's and PhD in physics at Tufts Institute of Cosmology, did his dissertation on the evolution of cosmic strings. And while many of us may spend our time thinking about what we want for dinner or what we're going to watch on TV tonight, he spends his time contemplating things like cosmic inflation, multiverse cosmology, string theory landscapes, multidimensional fluids, gravitational waves, and a variety of other quite esoteric concepts. Most recently, he's been in the press quite a bit regarding a fascinating new theory of his regarding what I'll refer to as cosmological neural networks, and we'll get into that. But all that being said, Dr. Vanchurin, thank you for taking the time out of your schedule to come on the show today and talk for a little while.
Yeah, thank you, Ira, for a very nice introduction. I want to correct you a little bit. I do sometimes think what I'm going to have for dinner, so that's
okay. So you have time to think about that stuff.
Yeah, so I still spend time doing that. But yeah, that's pretty much sums up what I've been interested in, and I'll be more than happy to answer any questions you have. The more provocative they are, I think the better it is.
Okay. Well, we'll start off with the non-provocative ones.
Okay. And anything at all.
These will be pretty non-provocative, but basically, at the beginning of the show, we typically hand things over to our guest.
Okay.
If you could just take a little time to introduce yourself,
Sure.
Tell us about who you are, where you grew up, how you got interested in science and theoretical physics, and sort of how you developed this amazing interest in cosmology and answering these questions that most of us don't think about too often.
Sure. Well, as a physicist and cosmologist, of course, I usually prefer to talk about theories, but since you asked, I will introduce myself.
Sure.
So I grew up in Russia, and I went to a mathematical high school where most kids who are interested in mathematics and live in Moscow would want to go to. And so that's kind of where my background started. But then I moved to the States, and here I became interested in physics, and I decided to maybe go and get a PhD in physics at Tufts University. And that was for many, they thought it was not a very smart decision. Instead of going to Silicon Valley and making money, I decided to do PhD in physics. But I was really always fascinated by science, and I think this is probably the only thing I'm good at, and anything else would make no sense to me. I mean, I had no choice. I had to become a scientist. But then at Tufts University, that I've met some very, very smart people.
Mm-hmm.
And one of them was my PhD advisor, Alex Lanking, and he introduced me to the difficult questions in theoretical physics, including multiverse theories that you just mentioned. And at that point, there was no return. Once you start, thinking about multiverse theories, inflation, cosmic strings, I mean, it's just you cannot stop thinking about those things. And so, after that, I went on to do a postdoc. Had a postdoc position in Munich with another Russian cosmologist, Slava Mukhanov, and that was a great experience as well. I couldn't speak a word of German. I still cannot speak a word of German. I spent 3 years there, but that was a very good learning experience for me. So I love that. And so But then I came back to the States and to Stanford University, where I spent 3 years as also a research fellow in a group with another Russian cosmologist, Andrei Linda, and that kind of so I've been passed around between Russians, and so I think that's kind of why I'm so much fascinated and interested in cosmology. But when I was at Stanford, I've met actually American physicists, Lenny Susskind, and this guy actually showed me that it is okay to know everything. Okay. And moreover, he showed me if you don't know something, you just go ahead and learn it. It doesn't matter how old you are, just go and explore new ideas. And you know, he has his ideas, I have my own ideas. But that guy influenced me a lot. And I think I would not be where I am now if it was not for all those people, of course. Yeah, and yeah, so I think it was if you want a short answer, there was no choice for me but to go the road I went. Anything else in high school wasn't just making much sense for me. I mean, if it's not science, if it doesn't have equations, I don't know where to start. For me, that kind of was a predetermined destiny, if you wish. But
it clearly has brought you to some very interesting domains.
Yeah, but the last 8 years I was in Minnesota, and here I actually, you know, was at the stage where I already got my professorship position, and so that's the time where you should actually, you know, explore the wildest ideas and the craziest ideas you have, and especially after you get your tenure. Okay, so so after I got my tenure, I mean, yeah, that sky is the limit. Yeah, so and at University of Minnesota, the last 8 years or so, I was again very much interested in multiverse theories and especially in paradoxes that appear there, and the paradoxes make us uncomfortable scientists. We try to resolve it, and by resolving them or understanding where they came from, we can make progress. And that's kind of one of the things I did with another American cosmologist, Alan Guth. We looked at one small paradox and said, okay, well, can we try to make sense out of it? And so that was one, you know, region of. Now, many people think that multiverse theories are not scientific and things like that. I think this is incorrect. They are scientific. They are scientific for a very simple reason. You can state your assumptions, you can do calculations, and you can make predictions, and that's how science is defined for me. And so, but also while in Minnesota, I've really been exploring different topics, like and that was, you know, from multidimensional fluids that you mentioned, the string fluids that I call it, to quantum computation, to studying different dualities, and then most recent work that you mentioned, it is very recent. I only started thinking about neural networks in the last maybe half a year, and that's my main interest right now. I was on sabbatical, so I was kind of, that's the time where you should explore your wildest ideas, and that's kind of how it's. I think it's interesting. I mean, as you mentioned, there is a lot of interest in the press about this for the reason I don't really understand, but apparently many people thought about something similar. And so, you know, when things click, even if you're not a scientist and don't come with the same background I do, but maybe some results that come out of my research are related to what you've been thinking about, then maybe that's perhaps why there are many people who are interested in contacting me, and I'm trying to reply to all emails and so, but if I haven't, I do apologize. But yeah, I mean, I'll tell you more about the theory itself later, but that's kind of summarizes, you know, your first, you know, question of, you know, who am I, right?
I'm always fascinated when I talk to thought leaders like yourselves, not just because, your mind works at, what I'll call sort of the bleeding edge of some of these domains, whether you're thinking about infinity or you're thinking about zero, nothingness, and everything in between. Could you two things? Could you take us just on a little, and once again, from a perspective of, I think of it, sort of the 12th grade sort of student that wants to go to college, and you want to sell me sort of why I should investigate cosmology. Sort of, can you take us through sort of that top line, sort of entry level introduction of sort of the different things you're looking at in terms of some of the things we some of us might be more familiar of, looking at issues with relativity and the basics of quantum mechanics. But at the same time, could you also just what is your typical day like in the cosmology world? Do you do any teaching still? Who sets sort of the cosmological priorities in the lab? We all have that sort of that Albert Einstein story. He was sitting there looking out the window and he came up with relativity. What do you do on a day in Minnesota?
Well,
You're looking at the window.
I am not Albert Einstein for sure.
Okay.
I don't think there are any living scientists who are even close to Albert Einstein. He was one of a kind.
Okay.
I don't know if you know about the Landau scale of genius scale, Landau genius scale.
All right.
Okay, so the Newton and Einstein, they're like at 0 and 0.5. They're the geniuses. Okay. Then all of the fathers of quantum mechanics are sitting at 1 or so, and I don't think there are any working scientists who have who are 2 or less. I mean, we're all we're all kids compared to them. Unfortunately, I don't know whether this will change or not. So Landau gave himself a grade 3, but then eventually he upgraded himself to 2. So maybe I'll change my grade later. So we're not there. So what Einstein did, he like really, nothing can be compared to what he did at this stage. Now, eventually, it doesn't mean that we cannot compete with him. We should compete with him. We should try to reframe the reality. We should try to reformulate the seed theories. We should try to understand better. And I think if you ask me about, well, how is my day divided, I'm either thinking about what is the right question to ask. And that is really important. Like, what is the right problem to work on today, right? So like, there are many problems. There is a cosmological constant problem. There is a dark matter that we don't know about. Inflaton field, we don't know where it's coming from. And I can keep going and going and going. There are many problems, okay? I cannot think about all problems at the same time. I will make no progress. So I'm trying to formulate a very small, a tiny problem, toy problem that I think is relevant, okay? And that takes a lot of time, because formulating the problem that you can actually, asking the right questions, I think the key. So if you can ask the right question, and I think that's what Einstein was very good at. He was just asking the right questions. I don't think he was like as good in manipulating mathematical formulas or not. I mean, everybody knows about tons of mistakes that he made. We all make mistakes. There's no problem about that.
Sure.
But asking right questions and then working and thinking about this question for years, even if no progress has been made, and that's what he was good at. I mean, just keep thinking about ask yourself an important question, keep thinking about it, keep coming back to it, put it aside, then come back to it. So that is important. And then eventually what you will realize, either the problem that you asked was ill-defined and you maybe want to change the problem, or you don't have the tools to tackle the problem. So you don't have the math tools to tackle the problem. Now, mathematicians are way ahead of us. So usually, okay. So maybe a right strategy, if you see there are tools are missing, and go and look for tools in the math literature, or like Einstein, try to reinvent those tools yourself. So creating a problem and then figuring out what are the right tools to solve the problem. I think those are the two biggest parts of my job. Now, teaching is fun, but it's not hard. If you taught one course once, it may at some point even become boring. okay? But you have to do this, because if we don't teach, we tend to forget physics, and if you don't use you lose it. And so it is a good exercise. I think it is very good that professors do both. They teach and they do research. This combination of duties is, I think, very productive and works very, very well. Now, it also depends on what kind of students you get. You may have very good students that ask very good questions, and then you learn a lot by teaching, okay? and that is the best type of learning. And I think, like all professors agree, if you want to learn something, teach it, and teach it to good students, and then that will work. So yeah, so my day is about that. It's most of the time I'm thinking either about the problem that I think is important, or how to solve it. And the second part is actually usually easier. So if you tend to kind of formulate the problem that interests you in the concrete terms, then the rest is just mathematics, and then we all think we can agree. Like physicists think they can agree on the mathematics. What they don't agree with, what the right question to ask, and that's where all of them, or we may not agree on the framework that we use to do calculations. So there will be people who will tell you you have to work within the framework of string theory. Mm-hmm. There'll be other people who will say, no, it has to be loop quantum gravity. And there is an emergent group who says, well, maybe gravity is just an emergent phenomena, and we should be just, trying to discover the new tools to see how gravity can be described. Maybe it's neither a string theory nor loop quantum gravity. There are also, there are many models, right? So you need to kind of pick your favorite toolbox, and then ask the right questions. So that's kind of, but that's the key. I think now, so if I wanted to sell it to youngsters, why would you want to do that? Sure. Now it's the time. We are in the exploration phase. Like for the last 40 years or so, physicists were very good in proposing new ideas, like string theory, like dualities. Inflation is a great another example. Quantum computation, so all cool ideas, and that's an exploration phase. We haven't actually used it yet to model the universe, right? We try to use it to model the universe, but things are not falling into right places yet. So that's a great phase. It means that if it was like 40 years of exploration, we are probably coming to the end of that explorationary phase, and right now will be the time where something important, something big should happen. That's my expectations, and be there. Be there when. So it's like I can imagine how people in the beginning of the 20th century thought and felt about quantum mechanics. That was like, wow! Yeah. All of a sudden, we all of them went through college, got their PhDs, they learned about classical mechanics, and they thought that was it. And all of a sudden, you get this new experimental result suggesting that no, there is a new and better paradigm which is emerging. And that, I feel like this is where we're coming closer and closer to this phase where actually we'll be not just exploring the ideas, but creating models that will better and better describe the universe, and on small scales, on large scales, the phase of actual progress that will be made. So that's my take on it. But there is another side of the coin. Not everyone who is thinking about becoming a physicist will end up being a physicist, right? Okay. So I think it's very important for youngsters, also younger students, to have a plan B, and that's extremely important. Okay, and here my recommendation would be, just have double major. Think about, okay, physics is cool and nice. It gives you a set of it provides you with the tools that you can use and apply. But maybe think about something else that you might be interested in, and you can directly apply, in industry. I don't know, machine learning that comes
Mm-hmm.
to mind. I mean,
Sure.
if I was a 20 years old student right now, that would be my choice. You know, double major in computer science and in machine learning, and then physics, and then theoretical physics. So those are the two things that I would be balancing in my schedule. But yeah, I mean, that's. I think we live in exciting times.
I
Right
agree
now.
with you.
It's about to come. So yeah. I don't
Absolutely.
know if I answered some of your questions.
Yeah, perfect,
No,
perfectly.
all right.
And
Good,
I'm going to
good.
have my oldest, my oldest son is in 12th grade now, so he's
He's okay. He's thinking where to go, right?
it's interesting for the purpose of our discussion because he's both interested in cosmology, but he's also interested in psychology. So
Okay. Okay.
we'll
Good. Good.
we'll
Good.
we'll
Yeah.
we'll, we'll get
Yeah.
to
Yeah.
a little
Plan
further.
B. He needs Plan B.
But so moving from that, thank you for
Yeah.
that second introduction also. So
Sure.
you a couple weeks ago, I think it was now, you
Mm,
published this very exciting this preprint, The World is a Neural Network,
right.
discussing this possibility that the universe at the most fundamental level has these
Yeah.
properties of a neural network. You also, a few months ago, you had a paper on machine learning. I'm not sure if that
Right.
was the preface to this, but so, and the general gist is, at my fundamental level, I understand is, you have these two worlds of
Mm-hmm.
Einstein and then the sort of the quantum world of
Mm-hmm.
Bohr and Heisenberg and these folks,
Yeah.
always been sort of a little battle to sort of how they come
Right.
together.
Right.
Observation is this potential third factor for things to bubble up or whatever. I know these are not proper physical
Right.
terms from the quantum domain. Take us a little bit through sort of this theory, and if you could also just walk us through too, because we talked about on the
Sure.
show
Sure. Yeah.
more from a biologic perspective, so the use of machine learning and neural networks in creating new drugs and things like that.
Right.
Take us through what you mean in your research when you think about neural networks
Right.
at the cosmological scale.
The right place to start to describe it is from with the first paper. Paper
Okay.
is not about physics; it's just about machine learning.
Sure.
And that was my initial objective. All I wanted, I mean, I had a half a year left in my sabbatical. All I wanted is to understand how deep learning works. It was very unsatisfactory for me to know that I have Alexa at home, but I don't know how it works. Right? I wanted to understand what are the Okay, actually, Alexa spoke up when I said that word. Okay.
Alexa, give me the secrets to the universe.
Yeah, so she's listening, right? So, anyways, and that was my first objective. And I said, okay, I know some physics. I know I have the tools of a physicist. Let's see if I can apply them, the tools, to model and understand how machine learning works.
Okay.
Okay. So we developed in physics very nice tools. One of them is statistical mechanics. There's a framework that allows us to do this. And I wanted to see whether I can borrow that framework, borrow that ideas, and describe how the machine learning works. Now, why did I think that statistical mechanics was relevant? Well, because in physics, we're having the same problem. We had the same problem. We know how to do calculations when there are a couple of particles bouncing around, when we have a small number of degrees of freedom. But when things become more complicated, when you put in a box 1,000, 1 billion of particles, then we can no longer perform computations, and one would think, okay, we have to give up, we cannot make any predictions. But no, statistical mechanics is a framework that allows us to make prediction about, a gas of molecules in the box, what will happen, how will it evolve from one initial state to another initial state. So the key there was to see in physics, the key assumption that had to be made is the number of degrees of freedom is large, lots of molecules. Then we know how to perform calculations. Okay, so something similar happens in machine learning. We have networks, but they're becoming increasingly big. There are more and more neurons that needs to be put in order to get the behavior, the learning behavior that we want. So that's the similarity. You have a very large number of particles in statistical description, and you have a very large number in machine learning. So can we actually use now the tools that we use in physics to understand how the machine learning works? And so that was the plan. That was the plan. For that, I realized that within the machine learning community, there were already some attempts to do that.
Mm-hmm.
So people did think about this. This is not a new idea to apply statistical physics. Yet I think I came up with a different, and I think in some ways better way of modeling and understanding how things work in machine learning. And for that, I first generalized the neural network. So now my neural network are not the ones that people usually draw in the picture where you have like feed forward, things only point in one direction. They can loop on itself, they're like recursive, and have many other more general properties that you may not even need to use, for example, for Alexa. So first I generalized the neural network. Then I took the limit of a very large number of neurons and started to make calculation analogous to what we do in statistical mechanics. Now, the outcome of the calculation in statistical mechanics is a phenomenological theory, which is thermodynamics. So you do those complication equations, but what you get out are not these complicated integrals that you take. You just get out the standard thermodynamics. There is a meaning of temperature, there is a meaning of pressure, volume, chemical potential. All of those things live there, and they are emergent. They are not fundamental, they are not microscopic. They're something that describe a combined behavior of large system with many molecules, many degrees of freedom. So I wanted to get that emergent behavior from neural networks as well. Okay, so now you take the limit, and then you see, and then you start seeing that something very similar emerges. You get something which looks like a temperature. You get something that looks like energy, and you keep discovering new things, and then at the end you see very interesting laws. So you have a second law of thermodynamics in physics that will tell you that entropy must grow. Well, it turns out that in a learning system you also have a similar law, but the entropy must decrease. Okay, it doesn't grow, it must decrease. This is the point. That's what neural network does. It gets rid of useless information. It tries to model functions with fewer and fewer parameters. It tries to decrease the entropy. It tries to make it, and this is just the equivalent to, you have a second law in thermodynamics that's completely physical phenomenon, and here you have second law of learning, which is in some sense, and you can ask, what about the first law of thermodynamics in physics? And then you can see what it is in learning. And kind of things are different, but the toolbox of ideas that you use to generate those different emergent phenomena are very similar.
Okay.
So I thought, okay, that's very interesting. You have this idea. Let's take it further. Let's see how things will behave not only in equilibrium when things equilibrate, but on the way to equilibrium. So like something non-equilibrium, a learning process. How does that work? And then you start seeing things that, gee, I think I've seen it before. What is it? Is it the Schrodinger equation? Okay, so now I see that in certain limits, I get a behavior. It's not actually the Schrodinger equation, but it's a Mandelung equation. And it has to do with the Bohmian interpretation of quantum mechanics in terms of hidden variables. But nevertheless, the picture, the description of a learning system close to equilibrium in terms of Schrodinger equation is correct. It is a correct approximate description of the system that has nothing to do with physics. This is just machine learning. This is just your computer. This is computer with many neurons and things floating around. Okay, so that point I already was done with this paper of borrowing the tools from statistical mechanics to model machine learning. And I said, okay, if I already start seeing something that I was not expecting, maybe I can turn things around. Let's see if I can model physics with neural networks. Maybe not only quantum mechanics, maybe I can also model and see an emergent behavior, which is gravity. Can I do that? So maybe you can have a neural network, and at some limit, it has an emergent behavior of quantum mechanics in equilibrium. Like if you wait long enough, the entire universe will thermalize and everything will be just boring quantum mechanics. And further away of equilibrium, when things haven't thermalized yet, you will have this long chains of neurons, and they flow around in space, and they And the question is, what kind of emergent behavior would they produce? Can you describe them further away from the frame? And it's a more complicated question than so. Quantum mechanics came naturally; it was just almost there. It was an emergent quantum mechanics, but also there. Getting to the general relativity was harder, and I think I followed kind of a route that string theory took, where in string theory on the microscopic level you have like strings wrapping around and they flow around and they are described by certain equations, which are number-Gödel Pauli coefficient. And so what I had here is, instead of strings wrapped around, chains of neurons floating around. So one neuron, which is connected only to one neuron. And so they are like one-dimensional objects. But the relativity comes from the fact that they are also follow the equations of approximate equations of motion, which are similar to the ones that we have with strings. So, I mean, there were many analogies that was suggesting me that, you know, string theory is relevant. But since I'm taking a completely thermodynamic approach here, like statistical approach, those strings were not quantum. So they were not. So the quantum was they're like more like hidden variables for the quantum theory. So if you want to connect it, so the quantum theory that were developed is emergent, and so as I said, it's like more Bohmian, where there are hidden variables. The reason why you don't know how your state vector will collapse one way or another is because you do not know everything about the system. There's something you don't know about this. There's some hidden. So this was kind of Bohmian approach, said like, well, it should not be that. It's not the many worlds approach where you take literally that there is a wave function and it dwells according to Schrodinger. In the Bohmian approach, or in the hidden variables approach, there are hidden variables that you don't know. And because you don't know how the wave function will collapse. Nevertheless, you can make predictions, and the predictions are similar to the ones that you would get with the just Schrodinger dynamics and the wave function collapse hypothesis that you adopt. So anyways, in that quantum theory, there were hidden variables, and those are the ones that gave rise to the gravitational and a stringy-like behavior that you would observe away from the equilibrium. So anyway, I think I might be getting too much into the details, but the big picture, if I am to describe it, there is a neural network, and you can study it in certain limits. So in limit where if you're considering small subnetworks, it's already equilibrated, and so since they're equilibrated, so they are in equilibrium and they closer described by the quantum mechanics. Now, on the largest scales, things haven't had time to equilibrate yet. And so the quantum mechanics is not the right description. And there other approximation needs to be made. And there where I expect the general relativity would emerge. So that's kind of like two different limits of the same theory, like one in equilibrium and the other one is further away in equilibrium. I also try to test in between, because we know that the classical mechanics is a good limit of quantum mechanics if you take a large action, larger system. So, and that limit was also smoothly shown. So basically, you will see that not in equilibrium where quantum mechanics is very irrelevant, but a little bit away from the equilibrium, classical mechanics and the Hamiltonian equations of motion do give the correct description. So again, I mean, I might be getting a little bit too mathematical for the audience that you have, but that's kind of the picture then.
No, but it's still, I think it's still very useful, because it shows, you know, you have this theory, but you also have the math. You know, obviously this doesn't happen overnight.
Has to be there,
you have this math, and that's always sort of been, you know, you have to be able to prove this stuff with. Although there's probably only a handful of people on the planet to understand the math, you get there. I appreciate that big sort of that you have both of those things covered, and it's fascinating. Listen, I understand a small part of it, but it's just fascinating hearing you talk about it and the passion behind it. And it's going to be very interesting, obviously, as you were mentioning, with sort of these different factions that are out there in this space, whether they're the string theorists or other folks. You know, obviously you take a beating when you first propose things like this, but that's okay. You know, you're young and you got time, and you're not afraid to push the boundaries on some of these things. I just, I'm the next couple questions, I'm going to go into stuff that, may not be directly related, but, let's just go there anyway. And you can say, we'll talk about this or not. And if
Okay.
whatever.
Sure.
About a year ago on the show, we had on John Joe McFadden from Surrey University in UK talking about the theme of quantum biology. And I know this is a very, when you're talking about sort of quantum things going on in sort of the wet and warm and macroscopic world of biology versus sort of the area that you think about, which is very subatomic and cold. There's, once again, talking about topics like magnetonavigation in birds and photosynthesis. And of course, part of what he talks about and studies is sort of Sir Roger Penrose's theories on sort of consciousness that he's worked on in the past with Stuart Hameroff. Once again, here we're dealing with sort of looking at the brain and the microtubules and so forth as sort of this quantum vibrational system. You're dealing with much more, I know it's probably not the right way, but sort of this cosmological brain. Let's say we're not saying it's a sentient conscious thing yet, but any interesting parallels on sort of the quantum biology front that you might want to talk about?
Yeah. The first thing I gotta say, and I gotta admit it, I don't know what consciousness is. Okay.
Sure. I don't think anyone else.
So I gotta admit that. All right. But then I think there is one observational fact that we've all observed when we looked at the simulation of dark matter filaments, and we looked at the picture of biological neural network, and they do look very similar. Okay, so we have this kind of observation, and many people made this observation. And so whether they are really related in some way, this biological neural network, whether the equations that describe evolution of a biological neural network is somehow related to the equations that describe evolution of filamentary structure or cosmic web, I don't know. It's a good question. This is a good question. And if it is, that would suggest something that I haven't personally thought about, but it suggests something that maybe there are really similar phenomena, similar equations. I mean, I keep talking about equations because that's how I think about things. You know, if I see a picture of something, I mean, tell me what the equation that describes it. So with this respect, I think there may be similarities between what happens in the biological brain that we see and what happens on a very large scales where I currently try to model gravity. So I've already said that I've modeled a general relativity, but I haven't modeled dark matter, but that's kind of next logical step. You want to see, is dark matter something that will generically produce if there is a cosmological neural network? So that's a good question. And if I am able to model the filamentary structure and dark matter, then that would be interesting to see if something similar happens in the brain. And now, is it consciousness? I don't know. Now, there is one speculation that I did make in the paper, just because I couldn't resist not to make this speculation. I said, if it is true that everything is just a neural network, then I think we should expect something like natural selection to happen on all scales. There is no reason why the natural selection should be confined to a particular length scale or to a particular time scale. Now, on the smaller scale, I would, instead of calling it natural selection, I say, well, okay, it's true that certain chains of neurons, certain shapes of neurons are more likely to survive. Yeah, and they will be there for longer. And the others ones, maybe like consisting of very long neuron chains which stretch around, they are less likely to survive and they'll be eliminated. Is it the natural selection? It is. It is because we have an evolution of neural substructures, and some of them stay longer, some of them get eliminated. Now, those substructures, the subnetworks, eventually may produce you something that we will eventually call particles, elementary particles, atoms. Maybe later, more complicated structures that we'll produce, we'll call them cells, or biological cells, or observers like us. So all this, I think, could be related in a way and linked to the natural selection. But in all this discussion, I'm putting myself outside of the system and seeing how would the system evolve,
Sure.
if it would be governed by, and then I would not be surprised if some observers like structures would form within this cosmic neural network, something that you would call an observer or a human or what's not, or a cell, and I would not be surprised that these things would form. Now, are they conscious? Do they have consciousness? That I don't know, right? So that's kind of the question is, maybe they do. Maybe that's all it is. Maybe, if you have some sub-neural network that is capable of performing advanced calculations and then can, communicate with like structures, similar structures, maybe that's what it is. That's what observers are, and that's how they, and that's what consciousness is. If that it is, then it makes simpler. All it remains, all that we have to show now then, that this is true, that these structures will form, and these structures will be more stable than other structures. And that's a difficult question, because as I said, the bigger your system becomes, the fewer mathematical tools we have to handle it. Now, but only in the limit where it goes to infinity, when we are talking about thermodynamic limit, we can make progress. So we don't currently have the tools to really do calculations for this scales where it's not too big, not too small, and their networks have very, very high complexity. So with this regards, I think there may be some truth to what those people are doing, but I currently don't have calculations to back it up and say, yeah, they're right. I mean, absolutely, quantum consciousness all the way. No, I cannot do that. I have to be honest. I mean, there are some calculations I've done, others I haven't done.
Hey, well, we'll add things to your list.
Right. Yeah, exactly. It's a huge list of to-do things. Right? Yeah, very good. Yeah.
Let's keeping along that path, and now, okay, so we went from sort of small to the universe. Now we'll go even bigger, and I want to segue into another area that you are focused on, the multiverse, which we describe as sort of this hypothetical grouping of all universes. Could be called different things depending on what we read: parallel universes, many worlds, so forth. On your website, you mentioned recent developments in string theory and cosmology point towards a new picture where our observable universe may be only one island in an infinite sea. And then you mentioned a variety of paradoxes, some which are quite complex. I think of the obvious sort of layman's paradox of, if we find the multiverse around here, it's in our universe. So anyway, can you take us on a short walk through the multiverse concept, sort of not the concept itself, but sort of what are sort of A, B, and C, what are the hot areas of multiverse thinking and the discipline, and at the same time, I'm going to throw this one at you too. That's the second part of this, and it's fine if we say, well, we don't know this yet, or we're not ready for this. Once again, I'm coming back to the mind again, and just in thinking about the multiverse, because I don't know how to think about it. About 6 months ago, we did an episode on a totally unrelated topic of delirium, which is this very weird mental state. It's sort of like Alzheimer's evil twin, sort of a short-term acute sort of confusion. And unlike other sort of psychedelic states, let's say, it's one that you don't know who you are. So you ever think about sort of waking up from a dream where you're not that guy flying around, whatever you're doing, you're you, and it takes you a few minutes to realize that you're still you. There was some very interesting parallels in thinking, like, is the multiverse, is it how we think about it, is it really we have a universe here and another one and so forth? Or is it sort of coming to your cosmological neural thinking? Is it another way that this network is thinking about itself, but it just doesn't? So anyway, take it away.
Yeah. Okay. Good. Yeah. So yeah, there are two theories, and I think I will tell you my view on this on both approaches. Whether they will eventually merge together, I don't know. So thinking about your mind that just wakes up and confused and doesn't know where it is, and then keep being I think that that's normal. That happens with all the babies that are born. I think that's
Sure.
what must be happening. I mean, they have a neural network inside them. I mean, maybe it's more advanced than the ones we have for Alexa, but it is a neural network, and it is confused because it doesn't make sense of what it sees around.
Mhm.
And then it may see a ball flying towards you, towards the baby, and it would make no attempts to catch it or move to the side just because it doesn't know that this ball will produce pain or anything. And so
Mhm.
the baby is just observing, and I call it learning. I mean,
Sure.
it's observing, it gets the input information, it learns, and then eventually it starts to make sense out of things. Not It's kind of learned how to behave in this environment. It takes time. It takes a few years, but then eventually it learns how to speak and then how to communicate. And then so at this point it made sense out of the universe. And I think it's an interesting picture. Whether I don't know whether this the brain of the entire universe has any coherent thoughts,
Mm.
like the baby does, or maybe just a collection of thoughts of all of us, and then really this big brain isn't really capable of producing any other thoughts. I don't know about that. So I think at this point, from my picture, it is not a multiverse. It is just one. Like if you want to call it a brain or a mind, call it whatever you want.
Mm.
Cosmological neural network is probably a better name. Now it is an interesting question to see whether this brain is actually learning, because there is no outside to that brain, and
Mhm.
so
Mhm.
if it was unsupervised learning, and it's possible that happens. Okay, so and here kind of my view would be that it is still not a multiverse, but a universe, unibrain, whatever you want to call it, the one neural network at all. Now, can you consider probability distribution of those universes? Yeah, if you don't know about every single neuron in that cosmological neurons, then the best way for you to model it is to think about ensemble probability distribution. It can be this brain, it can be that brain, or that brain. Here it is. Here is your multiverse. But the multiverse comes from the only fact that you don't know everything about that brain.
Mhm.
And it's okay. Then and then it is similar to what we have in one of the models of the multiverse, which is eternal inflation. So this is the
Okay.
one I mostly worked at. And so basically the model is that you have infinitely exponentially expanding universe, and things constantly move out of your horizon. And so you really have lots of patches, or what Alan Guth calls pocket universes in there. And then you live in one of them. Okay, and then you want to make a prediction. You want a prediction of what is the probability of having this value of Higgs mass, or what's the probability of observing this temperature, CMB temperature, and it's a random parameter for you for this ensemble of universes, for this ensemble of patches. Now it's similar to the mind because it's still a distribution, but the paradoxes arise not from considering ensembles, but from the fact we don't know what the right ensemble is, what is the right probability distribution. So, we say, okay, when we don't know something, we usually use cutoff procedures because it's infinite. Let's cut off the infinity. Let's do calculations and then take the cutoff to infinity. That's what we usually do in physics, but it doesn't work here. And the reason it doesn't work is because the expansion is exponential. So no matter what cutoff you make, most of the volume is right next to the cutoff. So you shift it a little bit, your answer changes completely. You shift it a little bit, your answer. So we don't know how to make the right predictions. Fine, let's just agree what the right prediction is. But then together with Alan Guth, we wrote a paper that even if you agree what the cutoff is, and you really try to carefully analyze what a person in such universe would experience and what kind of prediction for different questions he would have to make, you will discover there is still a paradox. So even if you agree what the cutoff is, and that's what we kind of work with him. So avoiding paradoxes in this picture of eternal inflation where things expand, I think is kind of probably won't be possible. So you'll encounter some kind of paradoxes one way or another. And that's very unfortunate because eternal inflation is is extrapolation of what we know about cosmology. I think like most cosmologists will agree that inflation took place. I mean, there's like very good evidences that this happened, and then we're just extrapolating it. You know, if inflation took place, it must have been eternal. It is a generic prediction of inflation, and then things start to fall apart. And so, and that's kind of, we have this one multiverse picture of eternal inflation where everything works fine until you enter the multiverse, the real multiverse of many universes, and it's not satisfactory. And this is one of the reasons why I started to look at the different options, just because, you know, the eternal inflation wasn't producing what we wanted it to produce. It gave us something very cool. I mean, it gave us the predictions of the spectrum of the CMB, and that was pretty cool. But it was just inflation. Once you make it eternal, things. So yeah, I mean, I think both pictures, whether you treat an ensemble of, you know, cosmological brains and think about this as a multiverse, or if you treat eternal inflation, both of them like a multiversal picture, and both of them kind of give you this feeling that there are, or modeling where there is many universes and you don't know in which one of them that you live. But they are different, and you would be doing different calculations in two setups. And as I said, eternal inflation is not as pure as we wanted it to be. However, I mean, there are certain predictions that we did do, and they were very good, but they mostly have to do with a low scale inflation when there were not, you know, no infinities. Fighting infinities is a struggle. I've been fighting with infinities for a while, and then so yeah. So if eventually we figure out that this cosmological neural network is infinite, that would be it. I mean, I'll give up. I'll quit physics, because that, I mean, I mean, it's like, it's anywhere you go, you again get infinite. But okay, some infinities are better than others. But what actually not good is to have this exponentially expanding space. Not good in terms of it's not a good framework when you try to make precise predictions.
Mm-hmm.
So I don't know. I haven't explored this question in context of the neural networks yet. But again, this is, I mean, as I said, there's a to-do list, right? Dark matter, quantum in the brain, and then so forth. So, and then the standard model. Then now we have this multiverse. It's a long, yeah. I mean, it's right, exactly.
What before we get to some of the wrap-up questions, I want to ask you one other thing, because I'm not familiar with the term, nor should I.
Sure.
What are multidimensional fluids?
Right. Okay. So that idea is actually more down to earth. Okay. So think about first cosmic strings, or strings, just one-dimensional structures floating around. They can be long, they can intersect, they can form loops, they can chop off loops, something like that. It's like a soup of this noodle. My son calls it space noodles, you know, because they look like. So you have this floating around. But then you can imagine a higher dimensional objects, you know, brains, and they're floating around. And then you can ask, instead of trying to develop a quantum version of those objects, and which is what string theory does, you're trying to say, well, let's again develop the thermodynamic version of it. So we know how to handle point particles floating in the box, and we know how to develop a thermodynamics of point particles. Let's develop the thermodynamics of the strings. Those can be protein molecules. Okay. It can be filaments of the filamentary structure in cosmos, right? Anywhere where you see one-dimensional or two-dimensional brains, you know, what would be their behavior? How would they be? How would they chop off? What kind of equilibrium they'll get to? And then you can study it using quantum description. That's what string theory would do when you consider path integral over all possible world sheets, what's not. Or you can take a phenomenological approach and say, okay, what would be a thermodynamic description? And so what would be pressure tensor? What would be, you know, temperature? How is there a meaning to temperature? Or maybe, and you see that there are more complicated objects and modeling has more parameters in it. But at the end of the day, you may be able to apply this string fluid models to study not just cosmic strings, but protein molecules, things that are, or they appear on
Sure.
in the lab in the smaller scales in condensed matter field. So that was my motivation, to see, not to go the quantum way again, but to try to see whether thermodynamic way. I mean, don't just take it as a first step towards developing. So that was our attempt that kind of produced very nice results. But for now, the question is, what is the actual physical system where this model of string fluid can be applied to it? So is it the protein molecules? Maybe they do experience behaviors close to strings. Maybe they can be modeled as string fluid, or something else. And here we kind of don't know yet. We kind of need to see an input from the experimentalist that would come and say, look, I mean, we have one-dimensional structures appearing in our lab. Can you describe those one-dimensional structures? And we say, yeah, we can describe it as fluids. They're different fluids, and so there'll be different equations. So it's not going to be Navier-Stokes equation, but something else that would assume that underlying structures are one-dimensional. So that's kind of the idea. But I think for that project, what's missing is to see where is this theory can be applied. We don't see cosmic strings on the sky, so there is not much to compare there.
Sure.
Moreover, there are some regimes which suggest that they will actually behave a little bit differently than what we have. But again, this is kind of why I think this is interesting direction. But unless we get an experimentalist who would come and say, look, I mean, we see that in the lab. Here is a one-dimensional noodle that is there. Then we're good. Then we can apply this. Yeah.
Really cool. Really cool. Thank you for that.
Yeah.
So what does a theoretical physicist, a cosmologist like yourself, like to do in your spare time when you're not contemplating infinity? I mean, I work in the biotech industry, so I love watching movies about time travel and space and all sorts. What do you do when you're not thinking about this stuff? Because you got to shut this down occasionally, right?
Yeah, absolutely. I love sports. Okay? I love sports. So I love playing soccer. Now, unfortunately, now is not the best time to play soccer because of the social distancing.
Sure.
I love watching soccer. This is like, I mean, I think I would have been a great soccer player if I wasn't a physicist, but unfortunately, so I love now jogging, any kind of sports is for me. Now, that's all good and cool, but I also have lots of kids, and so I still have to spend time with them. And so I tend to spend a lot of my free time taking them someplace and doing something fun with them, and whether it's hiking, go fishing, or something like that. But if you ask me what I would do myself, I would just I would play soccer all day long. And that takes my mind off for sure. Watching movies is great, but I usually fall asleep in the middle of the movie. It's very hard for me to watch any science fiction movies.
I can imagine.
It's like, and then my wife hates it the most, because like if they start speaking about black holes or something, and she looks at me and I'm like, oh, that's wrong. I mean, come on, why did they say that? And she's like, shut up, okay, just let them do their job. But the string theory, the Big Bang Theory show, that was pretty good. I liked that. So we both enjoyed watching it. So anyways, movies are great.
Wrap up question. You mentioned early on your PhD advisor being a major influence. You also mentioned Leonard Susskind. At this point, other teachers, mentors, friends along the way, anyone else you want to shout out to that really helped you keep on this path?
There was one physicist. He was my undergraduate advisor, Walter Johnson. He was in Suffolk University School, and who introduced me to neural networks in the first place.
Awesome.
And then I put it aside for 20 years, and then I can, oh, that was a good idea. So he influenced a lot, and I think I would not be a physicist if it wasn't for him either. That's one person. And then I have to name Alan Guth, because gee,
Sure.
this guy is really important for me. Whenever I'm trying to develop a theory, I always imagine him sitting next to me and kind of, well, of course he's falling asleep all the time, but that's beyond the point. Once he wakes up, he usually asks good questions. But what he does very well is he filters all the bullshit that you have. So basically, you can be telling him something for 1 hour, and then he'll summarize it, the most important things, within, I don't know, 20 seconds or so. And that's a good skill to have, be able to look objectively on your own calculations and see what is important and what's not important. So I think kind of his way of thinking about physics and kind of helps me a lot when I do my own research. So yeah, so those two more guys, yeah, I would probably give him, yeah, they're great. Both Americans. So I've named 3 Russians and 3 Americans. I think we're even.
Perfect balance. Perfect balance. Well, no, it's really, this has been a really fascinating discussion. A lot of it, obviously, over most people's heads, but you really did a great job at distilling a lot of it down and making it very sort of real world. So we could sort of, right. Not that we're all going to think about these things in our daily musings, but nonetheless, it's truly it's fascinating to see, as you were saying, sort of these decades that have gone by where things have been maturing, and then finally you have the ability, and the position you're in, to sort of ask the next question. So a really great time, and wishing you the best with all of these programs. For everybody that is going to be watching on the YouTube channel or listening on the various podcast networks, you've been listening to the amazing Dr. Vitaly Vanchurin, Associate Professor, Theoretical Physics and Cosmology at University of Minnesota, doing amazing things with cosmic inflation, multiverse cosmology, string theory landscapes, multiple dimensional fluids, and a bunch of other fascinating topics. Vitaly, thank you for taking the time out of your schedule to educate us. Thank you for what you're doing to move the field of cosmology and theoretical physics forward. But as we say on the show, thank you for moving the human story forward, because I think we're always going to come back to find the connections, whether we're talking about the infinite or the human situation. It's ultimately going to be connected. So it's really neat stuff, and wishing you, as I said, the best, and thanking you so much for your time.
Thank you very much, Ira. It was great. It was my pleasure. Thank you.